let me introduce the speaker, Dr. Abhinav Dayal. Dr. Dayal, right now he's a professor at the Computer Science Department at Vishnu Institute of Technology, which is in a place called Vishnupur in Andhra Pradesh. He's also a Dean of Advanced Learning, and he has been in in this place since mid of 2015. But before coming to Vishnu Institute of Technology, he has had a long career in the US. In fact, he got his PhD in 2005 from Northwestern University. Before that, he had his MTech in IIT Delhi, and he's got his bachelor's in 1999 from Birla Institute of Technology. So in the US, he worked with, he started his career probably with Wolfram Research, where he was a technical support engineer. And many of us are familiar with Wolfram. It's a famous site, focused on mathematics and algorithms. Then he worked for a number of years with IDV Solutions as a senior software developer as well as a consultant. But I guess his heart was always in the education sector, particularly in the education sector in India. So that motivated him to come back to India and join. So since 2015, he's been in Vishnu Institute of Technology. According to his LinkedIn, he's also a director and founder of Intelligence Technology Labs. I don't know much about that. Probably Abhinav Dayal can speak more about that. So today's topic is about machine learning, which is a hot topic. Many of us know about this topic, or are very much interested in this topic. So I will pass on the stage to Abhinav Dayal. Please, Abhinav.
Thank you, Arvind. So a very warm welcome to everyone, and a happy Teachers' Day as well. So I'll begin with sharing my screen. Okay, so today's topic is it's derived from a project we recently completed. Actually, we participated in a competition, an international competition from OpenCV, where they wanted us to utilize their OAK-D devices, so which is a combined depth camera and RGB camera and compute engine that can actually compute a machine learning model on device in real time, and wanted to solve some challenging problem. So at Vishnu Education Institutes here, we also have a section called Assistive Technology Labs, where we work on assistive technologies for disabled or elderly or medical scenarios. So we had identified a gap in, there are a lot of solutions where visually challenged people, products are built for them for their ease. But one gap was to help the the visually challenged person to actually board the bus. So we felt that this might be a good topic, so we participated, we were selected, and so we carried on implementing this one. So I'll start with a brief video that we submitted. We'll give you an overview of what we did, and then I'll get into how we started, what was the thought process, what steps were involved. Little bit we will look into the code as well, and I'll also share certain links, and we'll be open to questions. So I'll play this video. I have enabled the audio, so you should be able to hear the audio as well. I'm playing it now. Welcome from Team Vishnu Wizards. We are a university team at Vishnu Institute of Technology in Andhra Pradesh, India.
Only audio, sorry.
Spell.
I can't see the video.
Can you see the screen, like my screen?
Yeah, I can see the slide.
Yeah, it'll this slide is there for at least 10-15 seconds, so it'll get along. To board a bus. In our solution strategy, we have a computing unit, which is a Raspberry Pi, and a power unit inside a sling bag. and on the strap of that bag, the OAK-D camera is mounted. The visually challenged person is free to use a cane or any other device for general navigation in and around the environment. In our solution, we have 5 modes. The bus stop mode that helps identify a bus stop, and second is the person mode that finds the nearest person. Third is a road mode that helps the visually challenged to align in the incoming direction of the vehicles on road. Next is the bus mode that finds the approaching bus, and finally a bus door mode that tracks a bus door and helps the visually challenged board the bus. All of this is with a 3-button Bluetooth connected wristband, which currently is for demo purpose, but we are actually using a Blue Dot application on a mobile phone with these 3 buttons simulated. In order to identify the various objects and track them, we fine-tuned a MobileNet SSD for about 20,000 steps. Our classes involved the various vehicles that we find on Indian roads, the persons in different attires, uh, the bus door and bus stop and buses, bus routes, in the different kind of buses, old, new, rural condition, urban condition, crowded bus, uncrowded bus, etc. Our OAK-D pipeline used an RGB preview along with the depth and the neural network inference that drove the display. The depth and the inference together would drive the identification of road as well as tracking of bus and various object detection. All of these were followed by several calibration and heuristics and certain rules to actually drive the right kind of messages in a timely manner. Let us now actually see working of our solution.
In bus stop mode, bus stop found, slightly turn left. There is a bus stop in front of you. In person mode, there is a person about 4 steps in front. In road mode, road found, slowly turn right until no road detected. Slowly turn right until no road detected. Slowly turn left until road is found. Stay in this direction. Switch to bus mode. In bus mode, a bus is approaching at a distance of 55 steps. A bus is standing in front of you at less than 4 steps. In bus door mode, door is in front of you, slightly turn left. Door is in your front about 2 steps. A bus is approaching at a distance of 15 steps. In bus door mode, door is in front of you, slightly turn right. Door is in your front about 2 steps. Door is in your front about 2 steps.
In this instance, the user is completely blindfolded to mimic an actual visually challenged person and follows the directions given. Actually, it gave us a extremely humble experience of what a blind person goes through, and by doing this, it was such a thrill that we were actually able to help a blind person board a bus, as is evident from this video. It takes quite a bit of patience and listen to the instructions very carefully in order to meet the destination. Here, the user had to actually wait and analyze the instructions and then gradually move forward. It rightly told that the door is towards the left, and then when the user turned too much to the left, it indicated to slightly turn right, and eventually the user was able to board the bus. Thank you very much. We would like to take this opportunity to express. So, so this was the project. Let me. So rather than going through certain slides, I'll actually go through the GitHub repository, which is at this URL. My GitHub user ID is Abhinav Dayal /Dorai. So this is the GitHub repository where we have the code which is actually working, and I'll also quickly go through how we train the model, and also this is the Colab repository for the code used to train the model. And so to start with, let's look at the pipeline that we followed. So in essence, there are few steps involved in this kind of approach, right? Number one, we have to train a model that actually, in real time, it detects a few of the classes that we need. So we need to detect a bus, we need to detect a bus door, and there are multiple doors in a bus, so we have to disambiguate between the front, the rear door, and the driver door, and also emergency door sometimes in a bus. And there are different types of buses, and a majority of the models that are online were trained on Western style buses and clean roads, less crowd. So this was our first project where we actually used crowded buses, people around, and I'll take you through the the collection process of the data and how we iterated over to actually get a clean data. So other than bus door, to find a road, we need to actually also find other vehicles, like also to disambiguate between bus and other vehicles like an auto, a car, a two-wheeler, and like a truck, which is often confused with a bus, particularly from the front side, right? So, and also we want to identify persons, so a person. So these were all the classes that we actually started. And also for the bus, we also need the the route, where the bus route is. We didn't use the route currently, but we actually detected the location of the route. The next part which is remaining is to actually parse the route and identify what is written over there. So all of these classes we decided, and then we felt that we will collect the data set. So initially we started collecting data sets. So we told students, hey, collect the data for all of these things. So people collected, they went online and collected a lot of bus images, and mostly what people found convenient was to going to transport websites, and those transport people will actually provide very clean, very nice looking bus images, not that much noise. The background also will be very clean. Sometimes it is a scenic background and things like that. So they collected even few around 2000 images, but all of them were so clean that when we trained the model on that, it just did not work so well. So like in data collection, what is the best practice also, we and what we what the students actually realized after first iteration was that the data should reflect the real world scenario and not some kind of an ideal scenario over there. So that was the first observation. Second observation that we had was that there were multiple annotators. So when I talk of annotation, it is like, suppose this is the image given to me and I need to put a bounding box, that this is a bounding box and here is a person and this is a bus over here, and in this bus this is front door, and in this is a rear door, and things like that. So annotation is the process of actually identifying where in an image what is there, and we put bounding boxes around them. So another issue that we faced was that when multiple people were involved, and even though they were instructed with examples, when it came to actual annotation, different people follow different standards. So for example, I'll give you certain examples. Let me actually show you the data set that we finally collected. And okay, so these are some of the images, around 800 or 900. We started with data set of 2000 images, and then we reduced and reduced till we found a more cleaner data set and more consistent annotations. So for example, let us, I'll open one picture. Okay, so this is the image of a bus. So there is a bus here, and then we have a one bus, one front door and one rear door annotated over here. Okay, so now like what we instructed to the students was that we need a tight bound. So but some students, they would go and they would give a different kind of bound over here. For example, for this one, maybe they will take this as bus, maybe too tight, or maybe they take a bigger bounding box as bus, right? Similarly, for the front door, some people may give a bigger box and things like that, right? And certain sometimes people fail to actually annotate something which was already there. So these kind of differences actually confuses your machine learning predictor to actually predict the right thing. So then we reduce the number of annotators, and we all sat in one room in a day, and we said like together we will do. So rather than being online, we said, hey, all annotators should sit in one room, and we gave ourselves like a couple of hours and distributed 100 images to each, and then we said wherever there is a doubt, let's raise our hand and ask the question, but not just take any guesses. So for example, in this case, we only have a bus front and there is a car somewhere in the background. So likewise, we can see few more images. These are the cleaner images of the lot. So these are the images that were earlier collected. Then we went on to some more crowded images. This is a bus stop with many people around, different buses, night scene, very close up scenes as well, because people missed that. And when we actually board a bus, we are only seeing a very small part of the bus. We are not seeing the entire bus. So we need that kind of scenarios as well. These are all clean images. I'll also show you some scenario of crowded images as well. Let us see. So yeah, this is a crowded market scene. Now there is no bus here, but at least we have other categories over here. These are another few clean images. So these are our standard buses that we have in India, particularly in this part of the country. So another instance of a crowded scene. So this is another instance where people are crowding over, and the door is also crowded. So we took all of these scenarios and we annotated them. So once the annotation was done, actually, let me enable people to unmute themselves. Arvind, can you allow people to unmute themselves? Yeah. So if you have any doubt on this, please ask your questions in terms of, so key things in annotation is, one, it should reflect real scenario. Second, there should be consistency in annotation, and we need not take same kind of images. For example, I'll show you, a case in example. Say, for example, we consider this image, and this is so suppose I take 20 images or 30 images of the same bus in a same view, it won't make any difference, but same bus from different views is good, right? So there should be variability in the data that we are collecting, and if we are adding too much similar kind of data, it's waste of time, it's waste of annotation effort and storage and compute effort. So earlier we trained with over 2000 images, but outcome was very poor. Then we trained with 800 images with better variation, and the outcome was much better. Second was, second lesson is the consistency in annotation. That is very, very important. And for that to happen, whenever you are taking such a project, crowdsourcing annotations is not that great an idea because it creates variability in annotations. It's always important that we meet with annotators. There should be some manager who manages and evaluates and gets them corrected, because that's very critical for any kind of task. We don't want to confuse the system by saying, hey, this is annotation for this instance and this is annotation for a similar looking different instance, but the annotation is different, right? So we don't want to do that. For example, we don't want to give this as a bus bounding box here, or this as a bounding box here for the bus. We want to maintain consistency. Okay, any doubts thus far?
This is Ramnathan here. What is the annotating tool you used?
We use RoboFlow. So this is RoboFlow. There are many tools. VGG is also there, and we can even use that is open source. RoboFlow is not open source, it's a paid, but then it gives you up to 2000 images free, and that was good enough for us. It allows you to easily share with multiple users. We can create a project and invite multiple people to annotate with us. And it gives that, we don't have to define any kind of like in VGG, for example, we have to write a JSON configuration and do a lot of setup. In this case, we don't. We just drag and drop images and we tell these are the instances you have to annotate. And as people annotate new instances, it keeps creating its own annotations. So it's much easier, much user friendly, and it also provides support for different once we have annotated, we can export this data set to be applied to different. Suppose we want to use TensorFlow or PyTorch or some other framework, it can create data sets which are compatible with those particular framework or algorithms that we want to use. So it has those kind of settings as well. Third thing it supports is that it provides augmentations. So we can augment, for example, add noise, rotate, translate, crop. So different kind of augmentations it provides.
Okay.
One quick question. Hello, is it audible?
Yeah, yes.
In the annotations, are you guys considering the tires of the bus also as a separate, or I see in this image I'm just curious to know if tires are part of the bus or not.
Yes.
Because That might
Yes.
first reduce the size of the box. Second is for the visually impaired people, for the safety aspect, if the system is annotating that, hey, look, you are close to the tire, then it might raise some kind of warning to the visual impaired. I just got curious to ask.
Yeah, I mean, that's a good question, and very good insight. Probably we missed this, and we'll take care of this in next iteration of this work. But as you can see, we did include tires, but we did not annotate tires separately.
Okay, so
So
for the visually impaired, I think the biggest challenge is to board the bus. So when we are
yes,
boarding it as a visually enabled person also, sometimes we tend to slip because of the style of the Indian buses. So
yes.
that time, if because there is a in case of railways also, so there is a clearance level. So if the tires are coming closer to the stick of the person, then maybe for a safety aspect, the system can generate some warning or something like that.
I mean, one thing is like because we are using depth, we are giving a clear indication of how far the detected bus is. So if
Mm,
we are saying this is just one step ahead of your 2 step or 4 steps. So if he's too close, he will know that he is just one step, next step or 2 3 steps ahead. It is there, so that it will know. And the other thing which we did not focus on is we are we assume that the visually challenged person is actually using a cane or some other thing to act for general navigation. So this
mm.
project was just to identify the direction of the bus, whether bus is approaching or not, where is the bus door, and give a direction to actually move towards the bus door and not get lost.
Correct.
So
So
once he reaches closer, we are hoping that he'll be using the other sources like the cane or something to to actually board the bus.
right. So a very good kind of business use case can come out of it if a database has a inherent annotation that is a practical use case that many times you would have seen that a visually impaired person, he or she falls on the ground
Hmm.
because somebody else rushes in, and the people who are rushing in, they don't know the person is visually impaired or not. They assume it. And in
Hmm.
that kind of chaos, the person may fall down, and many times
Hmm.
they fall down. So if
Hmm.
you fall down and the bus is approaching, and
Hmm.
many times accidents happen, I'm just giving a practical example. So if the person is still holding the stick, because that's the only kind of rescue thing for the instrument for the person, and
Hmm.
the stick kind of gives a alert that the tires are approaching, or it's a safety mechanism that somebody can tell, because people can also see that the person is getting under the tires of the bus.
Hmm.
But if the system somehow recognizes this because of the visual computer vision and techniques and the annotation also there, like the stick knows that the tires are approaching, then
Hmm.
maybe you
Hmm.
can avert a potential accident.
Sure. Yeah. So
So,
and that can be done. I mean,
yeah, so that could be
fault.
a good
Yeah.
use case apart from enabling a person to board the bus. A use case could come out that to avert the
The
accident.
accidents. Yeah.
Yeah,
Yeah.
so that would
Yeah.
be one.
Right. Right.
Thanks.
Okay. Great. So
I have one question
yes.
pertaining to the image that you have on screen.
Yeah.
So we have here, let's consider two bounding boxes, one for the bus and one for the front door.
Yes.
Is there a consistency check performed either by the model or during training that the door bounding box is within the bus bounding box?
Yes. Yes. We are doing that.
Okay,
So
just wanted to know that.
yeah. Yeah. That's there.
How many images you had to annotate totally?
So we did around 850 as it says here.
Okay, 850 images. This is where you split the test and train.
Yes.
Okay.
And did you get balanced classes? Like you may be having 8 to 10 classes.
So that's the another thing that RoboFlow does when it so it asks us how many what percent of train, what percent of this thing you want. it balances automatically. So it has code within. So we don't have to write code for that if we use RoboFlow. There are also other libraries in Python that do that, but we didn't write code for balancing it. RoboFlow managed it for us.
But that depends very much on the annotations, right? What if you had too few cars in your data set?
So that's how we, while creating the data set, we actually make that there is a reasonable balance of classes over there, because this is data set we are creating. We select certain pictures. So as I said earlier, students had picked very clean pictures. So we deleted almost what 1200 around 1500 pictures we deleted what students have collected, and we added another 300-400 pictures with more classes over there.
What is the total number of classes?
So we have 11 classes.
So in a kind of a unsupervised learning, it is better to retain those noise, because then the system knows that this is not a bus, this is something else. So generally I have seen that people don't, whatever ground data is collecting, you don't get biased with the your pruning, human pruning. So generally in unsupervised way, you do not delete basically, right?
I mean, true, and we didn't follow the unsupervised route either here. So we went with the supervised approach completely.
Okay.
So in fact, this one, I feel that this is just a proof of concept. And if this has to really go into production or something, this maybe, a lot more training has to happen over there.
Sure. Good. Thanks.
So, okay, so let's move on to the next part.
How do you handle? Yeah, see, some buses may have multiple doors.
Yes.
Right? One in the front.
Yes, some buses have only single door. Some buses have two doors. And some buses have driver door and also emergency door. So we had this thing, as you can see, we have a driver door, front door, rear door. We have different classes over there. So if there is only single door, we only label it as front door. That was our just the annotators decided that if there is single door, we'll annotate it as front door only.
Sure, thank you.
Okay, so we followed like this tutorial over here. Somebody had written that to actually train a mobile net SSD, so single shot detection network using mobile net model. So this is the code for that. I can very quickly go through this, but this collab, this link I'll share with you, and you can actually read more from there. Let me see if I can increase the size. Yeah, should be readable by now. Okay, so we are just installing TensorFlow first, NumPy and TensorFlow. And then once we have loaded the TensorFlow, we are just we are using a pre-trained and model MobileNet V2 trained on Coco dataset, and then we are fine-tuning that model on our classes. So we are using transfer learning rather than learning from scratch, and that is another reason why less number of images is sufficient, because we are fine-tuning. A Coco dataset already has vehicles, people, it is already trained, it has learned its filters over there. So we are just fine-tuning on top of that. So so this is just we're defining our model config, and next we are setting up our object detection API over here. So this is just loading everything, the tools that are needed, just installing the steps over there. And next we are creating from the TF, we are loading the TF record files that we exported from RoboFlow. This is for our data set. Okay, these are our data records, TensorFlow data records, and it is converting into test and train. And these are our labels. So you can see auto, bus, bus stop, car, driver door, front door, person, rear door, route, truck, and two-wheeler. So these are our actually 11 classes, yeah, starting from 1 to 11. So this is the map text, what is our map. And next we are downloading this pre-trained model over here. So this one, so the directory is our local directory in Colab. So we are storing the model here, and then we are configuring our training pipeline. So this is just getting the number of classes, preparing the label map, finding the categories, and converting our own category index from the JSON file that is there. Then we are just setting up a pipeline that when to save our checkpoint. So whenever we are training a model, whenever we reach a checkpoint where the error is low, lowest till now, we are saving that point over there. So at the end, when we have trained for a number of steps, we will have the lowest error checkpoint saved. So this is for that. This is the actual pipeline here. This is our model and the matcher, which is actually taking the whatever the maximum argmax, so whichever probability is maximum, that one. And then this is an intersection over union. So basically if so what IOU does, I hope many of you may be familiar. So if this is my actual bounding box in my training data, and this is, suppose this was my predicted bounding box. So we find the union of these two and then the intersection of these two, and intersection divided by union, that ratio gives me kind of the error or the confidence that I have, not the error, the confidence that I have. So what is the IOU similarity? So that is the one of the similarity calculator over here. So this is all the pipeline which is generated, and then this is our training code. We are actually going ahead and we are running this. We are calling this object detection API to actually run the model with our model directory, our pipeline, and for these number of training steps and for these number of evaluation steps. So this is the actual training which is happening over here. And this is our Tensorboard. So a Tensorboard actually is a very neat way to actually monitor how your training is happening, and it puts all the whatever metrics you want to see in live, we can actually see that. So it's always good to use Tensorboard than to do your own charts or graphs. It's very handy, and Tensorboard is now supported not only in TensorFlow but also with PyTorch. So this is just to check we are running inferences over here. So our model is ready. It is saved through this way. So once this model is ready, next is how to actually build an overall system. And that we did over here in this GitHub repository. So I'll go through it briefly. If there are any questions on the Colab file, I can take it. Like 5 minutes on that before you move to this part.
Did you do any normalization, or RoboFlow does normalization?
Normalization is part of the model pipeline. So we just gave RGB image to the model. So MobileNet SSD definitely is doing batch normalization, and it is also it'll also be normalizing the images. We did not do that. That is part of the MobileNet SSD itself.
Okay. So it's not just the network, it is also does the normalization.
Yeah, so see, we did not create our own model. We are using a pre-trained model. So the pre-trained model comes with its preprocessor, and we just give the input in the way the preprocessor needs it.
Okay.
So it needed RGB images, and we gave that. So it by itself, it is resizing it to whatever size it needs, to whatever normalization it needs, and taking it further.
Okay. And what is your Tensorboard charts show? I saw some AR1,
yes,
AR2, AR.
Yes.
What do they mean?
Okay. So Okay. So these ones you are asking, right?
Yeah, what is that AR100, AR1, AR10?
So let me. This is our recall detection box is recall, and this is yeah, this is, see, this is average recall. AR means average recall.
Okay.
AP means average precision. This is mean average precision, MAP, and this is your with a 0.5 IOU. So at least the threshold is 0.5 for IOU. So this is with the 0.75 intersection over union. What is the average precision with that? And these are my AR means average recall.
Okay.
In this case.
The metrics that is being shown are for test.
Yes.
It's for test data set.
Yes. So we can actually, in Tensorboard, we can actually pick what we want to show here. And so we can even see the, the losses over here. I hope it will load because I'm not running. I opened an earlier file over there. So it's not connected, so I don't think it'll load.
So that's fine. That's fine. That's fine. Let's move on. Just curious. Yeah. Let's move on.
Yeah. So yeah. So here what we are doing, we are using blue dot app. So I'll go with this my.py. So this we are using this blue dot. We installed this blue dot library. So blue dot is also an application for iOS and also for Android. You will get a blue dot app over there. Now, whenever you run this blue dot app on a blue dot up, you load this and you execute, you create a blue dot. It actually starts connecting the Raspberry Pi with Bluetooth. So when you connect your Raspberry Pi with your phone via Bluetooth in the blue dot app on your phone, that app is connected to your program running on Raspberry Pi with this blue dot instance. Okay. So these are the event handlers. So when we actually, start connecting to a Bluetooth instance in our program, that's what we are, trying to do. So we are logging here that our Dorai is armed and this is our tracker. So I'll go through this code as well. So the tracker is actually running our pipeline. I'll go through this. What is the input and input width and height like? From the camera that is connected to our device, what is the width and height of the pictures we are getting, at what frame per second we are detecting. And then this is an alert service which actually raises alerts. For example, in the video you might have heard that road detected, turn right, turn left, or so those kind of alerts. And where we want to save our the outputs, for example, the whatever output we are generating, we want for test, we want to save the video or something. And this is the actual blue dot instance. So this will actually help us tackle the buttons that we press. So in a blue dot, we can configure multiple dots over there. So we can actually open the blue dot button. We search that over there. So this is the blue dot app. So on the phone, you can configure multiple buttons, and with each button, a corresponding function will be called when you are connected by Bluetooth to your device. So this is what we are doing. So let's go back here. Yeah. So we have configured the event for connection, and when we are disconnecting, we are actually disarming. We are, not using the tracker anymore. And similarly, this is to switch the modes. So the middle button is to tell what the current mode is, and then up button is to move the next mode and move to the previous mode. So, and there are different modes which are there. So yeah, so we have these alert modes over here. We can go to the top. Yeah, sleep, bus stop, person, road bus, bus door. So there are different modes, and one can in different modes the tracker will track the appropriate entities. So this is our alert service. I'll not probably I'll not go much through the alert service. More I'll spend time on the tracker. So we will go to the tracker. Okay, so this tracker is what is using the depth AI, and the camera that we are using is this Oak D device. Okay, so this is the camera. Actually, another site I'll open. Okay, so this device has a RGB camera. It has the two stereo cameras over there. So these cameras use epipolar geometry to actually calculate the depth in the scene. And then this is for our RGB. So we are using this RGB camera for detecting from the neural network that we have trained, the MobileNet SSD. And then we overlap the detections with the depth in order to determine how far that object is. And with those, the tracked object and the depth information, we are running a specific custom code over there to actually say in what mode what to detect and what messages to give alerts to in real time. So that's what is happening overall. Let's look at the tracker. So tracker actually works with kind of a pipeline. So as I am doing, I'll draw some of the things over here. So here we are defining a depth AI pipeline. In the pipeline, we are defining our inputs and outputs first. So we have this RGB camera. So we are taking input from RGB camera. And then there is a spatial detection network, which is our MobileNet SSD, in this case, MobileNet Spatial Detection Network. So this RGB will go to this our MobileNet SSD network. The input from RGB should go from there. And then we have our left and right stereo pair mono cameras. These are not RGB, they are mono cameras over here, only single channel. And then this will go to my stereo depth calculator, right? And then the output of this MobileNet SSD will actually go to an object tracker. Okay, so now this stereo depth calculation and object tracker are a little bit related in depth AI. And if we try to familiarize ourselves with what we call an epipolar geometry. So epipolar geometry means that rather than a single camera, we are trying to determine the geometry from multiple cameras. Say in this case, 2 cameras. So we have these 2 cameras. Their image planes are parallel to one another, but they are slightly at a certain distance, which we call the baseline distance, and they are calibrated. That means we actually know in real world their images are maybe at these many centimeters or these many meters apart. In this case, their baseline is 5 centimeters, the camera that they have created, right? So any 3D object, any point in the scene, suppose I'm looking from this camera, suppose this is the point on which this object is visible here. Now this point maps to the same line in the second image. Okay, so it is like obvious because all points on this line will project onto this point in this image, but all of them will point to different points in this line on the second image. Okay, so now what we have to do is we have to find, okay, what point here will map the point on this line. So in order to do that, we do similarity detection. We detect small patches. So we take a small patch here and we detect which of these patches is most identical with this patch. And then so for an x coordinate here, x left, I find the corresponding x right, and x right minus x left will give me the disparity. Okay, and in fact, the closer the object, the higher will be the disparity, and farther the object, more with lesser will be the disparity. Like we observe while moving, when we move in a train, the objects which are near to us, they appear to move fast because disparity is more. But if there is a mountain or cloud far, we don't even see it moving. It's over there. So disparity is very less for further objects. So once we have found this disparity and we know this baseline, we can do similar triangles to actually find the actual 3D coordinate of every point in the image. So that's how depth is calculated in a scene. And similar thing happens in object tracker, because this RGB image, when it, creates a mobile net SSD and it gives a, for example, in this image, this frame, I would say, it detects, okay, bus is here. And this is frame 1. In next frame, again, frame 2, it again detects a bus. Now, because since there is a already coded algorithm on the device itself that detects the similarity of these patches, it will detect, okay, this patch, is it similar to this patch over here? And if it is similar, it will say, okay, this is the same object. So it will track, it will give an ID to this object, and it will track the same object over time. And in fact, that is what we are using to denoise the thing. Say, for example, if bus is detected here, and then we confirm that bus is there when the same detection happens over a series of frames, maybe over past 4 or 5 frames or 10 frames, something like that. So so we do that over, and when we are confident enough, yes, it's there, and then only we raise an alert. So it kind of eliminates the noise in the system. So this is the the overall pipeline. And next, all is just here linking. So these, we have defined our sources. So I have discussed these parts. So similarly, we are creating links. So it is just drawing my lines from those boxes. So these are all my boxes. Okay, now I'm drawing lines to connect those boxes. I'm connecting the wires here next. Okay, so X out RGB is a link coming out, and tracker out is a link coming out from a tracker, like that. So we have created these links, and then we will be defining properties for each box, like what is the properties for my RGB sensor, properties for my mono left and mono right sensor, properties for my spatial detection network. For example, where is my neural network, where are my model weights over there, and what confidence thresholds I want to use. So I can use different thresholds for different classes. So I may want to detect a bus with a threshold of 0.5 and a person with a threshold of 0.2, something like that. So we can use different thresholds over there. And in set blocking means that if nothing is detected, should I block or should I carry along? So we are setting blocking to false. So we don't want to block the system. It should carry on. And so similarly, these are the depth thresholds. So these values are in centimeter. I'm looking from 1 meter to 500 meters. No, it's in millimeters. So I am using like 0.1 meter to 50 meters. Okay, so this is the depth range which I have calibrated as. Similarly, what objects I want to track. So in this case, I only want to track the bus, because once I have the bus door, the bus route, everything is inside that bus box. So I only need to track the bus, and once I have tracked the bus, I will track the other thing. So even though there are so many classes we are doing, but we are only tracking one in order to save on compute time as well. So this is configuring the object tracker. And now these are, this is the linking part. The left, we are linking to the stereo left input, and stereo right, the inputs are going over there. The camera RGB is connected to my mobile net SSD. Object tracker is connected to the RGB output, and the tracker out, the input of the tracker out is going to the output of my object tracker. So now once I have defined all of these, like the stereo depth is also calculated. Next we have, this is just to display, the OpenCV display code is here. So we are displaying a rectangle. So this is the frame, which is the actual NumPy array of the OpenCV image. And this is my CSV writer, because we are also storing CSV for each frame, a CSV file, just so as to post process if needed. And this is my frame counter, etc., etc. So let's go through these are my label colors for each class. I have a different the label format in OpenCV is BGR and not RGB, so blue, green, red. So for each label I want to use a different color, and we are creating a rectangle for the overall label in the label color, and we are putting the text, and this is the text rectangle. Okay, So this is just to draw those bounding boxes on my detected thing, and this is to write my CSV record for the detected thing. Okay. So now we are running this pipeline. We are connecting to our OGD device. So with depth.ai.device with this pipeline. So this is to instantiate a device which is already connected via USB to my Raspberry Pi. And we are loading this pipeline on that device, right? And then we are getting what is my preview, what are my tracklets, like the objects which I am tracking, what are my neural network and my depth outcomes here. Okay. And this is to actually output the video in OpenCV. We are using the 4cc video writer with this MP4 codec over there. So just initializing our outputs. And so if my blue dot is connected, then only I want to do this. If it is not connected, then I don't want to do this. So finally I get the trackers, the neural network outputs, the depth outputs, and then I am so what we are doing here, we are just taking the the tracked data. In this case we are tracking the bus, right? And then we are finding the unique. Suppose in case there are multiple detections which might happen, so we are finding the one which is like the maximum around that. So what we are doing is we are intersecting the detected rectangles, and we are finding that if the intersection between the two is greater than a certain threshold, so if the overlap is beyond certain %, we are saying that these are same detections. Okay, and those we are finding the one with the maximum area, so we are disambiguating multiple by just a single one over here. And same thing for each object detected in the neural network. Okay, then we are filtering objects by bus. Say for example, depending upon the bus that is tracked, I need to identify the bus door, rear bus door, front bus door, and the route. So we are finding those bus objects over here. And so our objects are our bus objects. And apart from that, we are tracking bus, person, vehicle, or bus stop. And in vehicle, we are combining truck, two-wheeler, auto, and things like that. And the way currently we are detecting a road is, of course, if it's a completely empty road, our algorithm won't work. Currently, we are hoping that some vehicle will be driving on the road. So if there is any vehicle detected, then we are saying that it's a road. So now we have to face the person in the direction of the incoming. So wherever the road is detected, we keep asking the person to rotate to the right till no road is detected. And when no road is detected, we ask the person to rotate slightly to the left till the road is detected, because then the person will be facing the incoming direction of traffic to wait for the bus. Okay, so then here we are, if there are certain detections, and so this is the rest of the code to actually handle those kind of things. So we are passing our objects, this entire objects which we have created, to our alert service, and the alert service is actually finding, okay, what it is maintaining a history of itself for last 1 minute history we are keeping, and then in that 1 minute history is tracking, okay, if bus is coming, this is a consistent bus over there, and it is issuing alerts that way. Okay, so I think in interest of time, I'll stop here and wait for a few questions.
Yeah, very quickly, Sanjeev here again. The alert service, I just want to know what is a end channel? Is it like visual alert? Because we are talking
about... No, it's an audio alert. It's an audio alert.
So how do you generate the audio and just...
So in Raspberry, so for example here, there will be a... So say message is self.speak. So this speak method is actually, we installed Pico 2 Wave on Raspberry Pi. So which actually takes in a text and converts it into speech. So we are, running this command.
Okay. So this would be like female voice generated or male voice generated. Is there any control on type of message like?
So by default it is female voice, but I am sure we can do more. In fact, now there are with this very fast performing neural speech engines. Many applications are coming. By far, Pico 2 Wave is more realistic. There are some others, but the sound is very robotic over there.
Right, right.
But the
So
Pico 2 Wave is quite better than the rest.
okay, so then again, that means you have kind of coupled it with Pico Wave. There might be some other voice synthesizers in the market,
Yes.
or in the research world. And second
Yes.
is it multilingual? Because we are assuming it is English, right?
Right now it is English, but we like there is probably in Pico 2 Wave if you search this one. Wave language setting. I'm not sure. I didn't even check that because we are only doing a experiment when we only use English. So we didn't. So maybe that is something we might want to look up. But certainly, one of the challenges that we are using Raspberry Pi, which is a low performance hardware. So we cannot run very extensive thing over there. But another we also got recently a Jetson Nano from NVIDIA as a gift. And that has a much better performing hardware. In fact, it has a GPU as well on the device itself, and it is as big and with the same voltage specification as Raspberry Pi.
Okay. So I was asking because if you have heard of there is a device in Japan somewhere which is like very small device, and it converts any speech to any speech, any language to any language. So the point being that kind of capability are very much there in the firmware. So as you have got in the NVIDIA, so I was curious that in the Indian context, now we have multilingual, right?
True.
So many languages are there. So maybe as a scope of improvement, if that open source firmwares are there, then you can incorporate. And I don't know whether if it is Pico Wave is having that capability, or how flexible is the code to integrate those capabilities.
Yeah, true.
Okay. Good. Excellent.
Another way that things work is like, because the messages that we are doing are more or less of similar type, only the data might change, like turn left, turn right. So these are specific instructions, only the numbers might change, 50, 55 or things like that. So what people do is they generate static text in multiple languages, like speech files, and store them and just play them in a certain order. So that's another way. Actually, many devices, rather than generating speech on the fly, this has been the age-old way to do it. So that's another straightforward way. If the messages we are doing are just command-oriented, very small and simple, but if it's a general speech, then yes, we need to do something more complicated over there.
Correct. So to bring it to the production or make it as a product kind of thing. Because if you see the actual scenario in public, right? So you see somebody standing on a bus stop who is visually enabled, and you find a person who is trying to board a bus who is visually disabled. And then there is a sequence of instructions on the fly from human to human.
Yes.
That slight right, slight left, up, or take some help. So that is where I think if you leverage on the speech capability, then this will really do wonders.
I mean, actually, I was actually surprised because I myself blindfolded myself and tried this, and I was actually able to board the bus. In fact, because the visually challenged person would be more used to the surroundings. Like that person maybe even easier, but it was. I was a bit slow. In fact, the last the yellow bus video, and I only tried it in a simple setting, but I guess there is a lot of scope.
Yeah, so we are slightly delving into the realm of multi-signal processing, right? So if you see a visually impaired person, he or she, their faculties of deciphering the speech, understanding the speech is enormous. Like they can decipher better than a normal human.
Yes.
So I'm just wondering, do you take inputs from the speech recognition also?
Not right now in this, but yes, it's currently we have these buttons, right? So instead of that, we can also do speech recognition as well, but we have not implemented that. In fact, in our ATL, we have done it as another project where we are doing speech commands based. like home automation for the disabled.
Okay.
And
Okay.
another one we have like other than the like we have a cane with a RF sensor. Other than that, we also have innovated in a belt which the visual challenge person can wear, and through vibration alerts they are getting a certain sense of direction, whether to turn
So,
left or right and things
right.
like
So
that.
that could be some kind of elite customers who are there, like who are terminally ill patients in the home care kind of thing. But this use case is generally very good in a kind of rural setup where you find many visually impaired who are poor people and who just have a stick and a cane. So
Yes.
I think and considering the population in India and with the variability of various states, I think for the bus database which you have, if you just augment it with a speech, then it will do wonders, I guess.
Yeah. Another thing which is coming up now, like in most of the modern phones, even the cheaper ones are coming with multiple cameras.
Correct.
And some of them are even enabling like calibration with stereo depth. So, I mean, that's how, for example, the modern iPhones and these, they detect your face and disambiguate it against a picture of your face. So, because they get the depth information out of there,
Right.
so they're able to
So
do
this
that.
will
So,
this could really who is this solution attempted by anybody else in the Indian context, or I just
so
not really.
particularly this one, if we search, like as I said, this was a novel problem because the way people have identified the bus and which bus to board, that is there, but actually directing the person to board a bus, and that was not done. So we found a gap over there. So we proposed this problem statement in IIT Delhi, and also now in IIT Hyderabad. There are several projects that people are doing to for the visually challenged, and the way they do was for the bus identification, so which bus to board, whether it's the right bus or not, and even alerting to the driver that I am a visually challenged, please wait for me, I want to board this bus, to communicate that kind of thing. So
So do
those
you
kind of
find
things have done.
enough government support from this if you want to take the project further on these lines?
Probably we
I would
can
like to cut in at this
We'll
point.
take it offline, yeah.
yeah, sure, we'll take it
Yeah,
offline.
sure. Thanks so much.
First,
So the
Sanjeev to hold on.
Yeah.
See if others have any questions.
Sure. It's
Because it's
the link.
becoming more of a discussion.
Mm.
So others, please, if you have questions, you can raise them now. Keep it brief. And if there is more time, we can have a discussion.
Yeah.
A quick one. How is that you adopted a transfer learning and any customization you had to do?
Customization in the sense we only prepared our data.
Okay. Otherwise, our pre-trained model gave you decent results. You didn't have to do any tweaking.
Yes. So particularly like in transfer learning, one very important thing to note is that we cannot take a model trained on completely different kind of use case and then learn it to something else. For example, I cannot take a model trained on medical images and transfer learn with this. So that won't work. So we picked COCO dataset because the kind of images the COCO dataset is working is similar. It is working with outdoor images. We are also working with outdoor images. They're also having similar kind of classes, vehicles, people, things like that. We are also having similar kind of classes over there. So therefore that would work.
And you had some specific, particular labels to your problem statement, right? For example, bus door may not be there in COCO dataset.
Yeah, bus. So several of them are not there. For example, even bus so truck and bus. Most of the images that COCO dataset is trained upon is Western scenario images. So if we actually look at our labels over here. Yeah. So auto rickshaw is not there in COCO dataset. Bus is also not there. Bus stop is definitely not there. Car is there. We are doing car. Then different type of bus doors, driver door, front door, rear door is not there. Person is of course there, and route. Bus route is not there. And then I think they do motorcycle rather than two-wheeler. But then we expanded two-wheelers to different types of two-wheelers that we see in India.
So how did you manage to train for these new labels without tweaking any layers?
Yeah, so see, we are not because the model itself is capable to do these.
Oh,
And
new label.
so like for example, it is already training for similar kind of models, and the way this understanding of vision based models will work, that the middle layers, so we start from initially like small features like lines and those kind of things, and then we move to textures, and then from textures we move to parts of objects, and then from there we move to actual objects. So we believe that even we are replacing the classes, but initial few layers need not be tweaked much, because parts of objects and all are quite similar. What need to be tweaked is towards the final, the later end point. But in this case, we did not even freeze any of the layers. We just fine-tuned the entire model, and we ran for around 20,000 steps. So again, it depends upon what model we are starting from. If we are starting from a very different model, we might have to use differently. Maybe we might have to add our own final feed forward network, or add our own layer later on, but it completely depends upon which model we are starting from and what is our use case. So
that makes perfect sense. So you trained to the complete new set of weights. You did not use the pre-trained weights.
We started from pre-trained weights and fine-tuned them to the new sets of weights.
Okay, thanks.
So now in your testing, did you get precision and recall for each of the classes? You might have found that for some classes the performance is poorer.
That's a good question. That's a good question. I think we have to post-process the output into finding the actual for each class separately. And I'll have to rerun that thing to actually load the Tensorboard. So time is not there for that, but definitely, now we are working on a paper for that, and all of these things probably we will be finding and very soon publishing it.
And I saw in your code that you have a FPS of 10. So
yes.
Is that kind of a limit that the Raspberry Pi can handle?
No. In fact, it can do up to like 25-30 was also working. The reason we used 10 is because one, that's the visual acuity for our vision system. Like even though we see video at 30 or 40 or 60 frames per second, but to a human eye cannot disambiguate between multiple frames at a faster rate than 10 frames per second. So we said that we'll use the same one. So as to avoid too much computation on the Raspberry Pi as well, so that the other processes can also get time. So because we have limited compute resources and we wanted to actually save on compute.
And the mobile SSD, which does the object detection, I believe it is doing on a frame by frame basis. It doesn't have any memory from the previous frame.
No, so memory is something we are adding.
That you are adding as part of object tracker, isn't it? The tracker.
So object tracker is tracking, but beyond that also we are adding a 1 minute. We are storing 1 minute history, and our alert service is using that history to actually eliminate noise and false kind of something that spurs up all of a sudden and that goes away.
Okay. But the mobile SSD itself doesn't use that memory. It does it
does not. It does frame by frame.
Okay. And last question is, you have these different modes. What I understand is, I'm not very clear. Is the switching of modes automatic, or is it triggered by the user using the blue dot? Yeah,
it's triggered by the blue dot. Switching of modes.
So what is the justification for that? Like, why can't why can't the model automatically switch the modes?
So basically, like if we do automatically switching of modes, we don't know like if the person wants to actually do that. So the idea was, say for example, if I am in I'm waiting for a bus and the bus comes, maybe that is not the bus I want to board in. So I don't want to switch to bus door mode. Maybe I want to wait for the bus. So we didn't do the route part because we didn't get time to do that. We did detect the route, but then to actually read the route and all, it was very difficult. The reason we didn't do it was in Indian buses, it's very poorly written, particularly in local buses in the area we live in. Mostly it is non-existent and people know somehow that this bus is going somewhere. So what we felt was that, the person will actually, if he need to board the bus, he will ask somebody like where this bus is going or something like that. And then if he decides to board the bus, then he will switch to that mode. So with that reasoning, we left it open. We didn't switch automatically because then we need to be very precise. Yes, that's what the intent of the user is.
Okay, got it. Thanks for those clarifications. Any questions from others?
Quick question.
You were sharing that notepad where you wrote that.
Yeah, here it is.
So can we have that slides or as a
the video link I'll share.
Video link,
yeah, it's on YouTube
okay.
already. So let me
Yeah, we'll take that offline. I will get the video link from you later.
Yeah, fine.
It will be part of our when we upload the video to YouTube, you'll see it there.
Yes.
What is that 1 minute history? How many frames are there?
So 10 frames per second. So 60 seconds, 600 frames we are saving.
Okay, you use the 600 frames.
Yeah,
good.
It's a queue. So 600 length queue. So that goes over there.
Yeah. For what purpose do you save it?
So to remove the noise. Suppose I detect a bus and then I'll keep checking like whether this was detected earlier or something like that. So so to remove the noise from the detections.
For object tracking too,
sometimes
right?
Sometimes what happens, an auto will be detected as bus, but but then over successive frames it will remove like the noise appears for a short time.
Okay.
You must be using the 1 minute history for object tracking as well, right?
So the object tracking is also kind of built in the depth AI pipeline. So we are the tracking of object we are doing from there, but on top of that, any other noise we need to filter. We are using our history for that.
Okay. That's an interesting project. Thanks.
Okay. So thank you, everyone. So regarding the the startup that I have, what Arvind said, it's again tuned towards education domain, and we have been working with many students here. And one of the challenges we faced was that the students who were technically good, they actually were failing because their communication skills were bad. So first product we launched was this skill2030.com. And this is for communication skills for engineering and science students. And we are also working towards a more, a learning system that is more apt for like rural audience or people who need more of kind of a support and not that much self-motivated. So we are working towards and researching towards systems for that. So of course I'll end at that. So I think time is already.
Thank you so much, Abhinav, for this wonderful talk. It was particularly interesting to me because I haven't worked that much on machine learning, particularly image processing. So it was a very useful talk. This video will be available on our YouTube channel shortly, along with all the relevant links that Abhinav has shared. Thanks everyone for joining us, and once again for Abhinav, happy Teachers Day.
Thank you everyone.
Thank you, Abhinav.
Bye.
Thanks.
Happy Teachers Day. Thanks. Bye.
Thank you. Bye.